Hi everyone, my name is Minghao Guo. I'm currently a first-year grad student at the Department of Astrophysics in Princeton. And this is one of the works that I did when I was undergrad at Peking University in China with Professor Louis Ho and Min Du, who is currently an assistant professor at Xiamen University in China. So this work is about a new channel of bulge formation via the destruction of short bars. So galaxies are generally considered as compact stellar systems comprising a fast rotating disk and a more slowly rotating bulge. So then a very fundamental question is, how do these bulges form, which is pretty important in understanding the evolution of galaxies. So observationally, bulges can be separated into two different types, classic bulges and pseudo bulges. So from a morphological perspective, classic bulges are highly condensed, featureless thirds, while pseudo bulges are more flattened, having lower surface density, which is illustrated in these two sketches. So classic bulges are thought to be the end products of major mergers of gas-rich galaxies. But other processes besides mergers may also contribute to growth of classic bulges like misaligned accretion of gas and clumps coalescence. Pseudobulges are thought to form through secular evolution of large-scale disks of spiral galaxies, in which bars might be a key agent of angular momentum redistribution. So bars, which here is some little background about barred galaxies. So bars can funnel gas efficiently into the central region of galaxies by bar-driven shocks, forming some like nuclear rings, disks, and bars. And nuclear disks are like to be classified as pseudobulges morphologically sometimes. So in this study, we run some n-body simulations, and the evolution of the models can be separated into three phases. So in phase one, the bars or the boxy or peanut-shaped bulges form spontaneously. So at within the first 3 gigayear, all the models form like bars and the boxy peanut bulges spontaneous due to their internal thermodynamical instabilities. So these bars have reached the steady state. And at this stage, the black hole is still small and has no significant effect on the evolution of the hosts, as shown in the edge-on images of the figure. So then at phase two, the short bars are destroyed due to the growth of the black hole after we add in a black hole whose mass is roughly 0.2% of the total stellar mass. Then the short bars are completely destroyed within like a half a gigayear or so. Then at phase three, it will form some steady, more like a classical bulge morphology, and it reach a steady phase. So the morphology is unchanged until the end of the simulation. And then we use scale fit to investigate the morphological structure of the models. So here the disk is described by exponential profile and bulge is described by statistical function. And we use both the statistical function and the modified first function to describe the bar. And we also tested the effects of inclination angle. So here the figure shows three different models. S2b is a spiral galaxy with two bars, an outer bar and an inner shorter bar. And SBA is a case with a short inner bar, only a shorter bar. Well, SBB is the case with a longer bar. And here we show the simulation results, our model and the residuals and the 1D profiles of the different components. So here, the basic the basic point is like after we did this decomposition, we can get the evolution of the central bulge. So using the morphological decomposition, evolution of the mass function and the therapeutic index can be shown here for the three models. And here we vary the inclination angle from 0 to 45 degrees. Then the bulge mass of the first two models clearly increase significantly after the short bar are destroyed and reach to the value of roughly 1/3 of the total stellar mass, or even sometimes 40%. And although the two short bars differ greatly in strength, they evolve similarly. Then the destroyed bars become part of the bulges. Then the therapeutic index increase to a value from like 0.5, 0.7 to around 2 without involving any external perturbations. And a therapeutic index of 2 is generally used as a criterion for defining classic bulges. But sometimes there are also some other works like Guo 2019 proposed therapeutic index 1.5 might be a better criterion. And as a consequence, the formerly boxy and peanut-shaped bulges takes more of appearance of a classic bulge. Then for comparison, the bulge of a single large barred case has changed a little. So all the results above are roughly independent of inclination angles and choice of bar function. So finally, after 4 gig year, all the bulge evolves slowly. And then we examine the simulated bulge of the 3 scaling relations that have been commonly used to classify bulges. So the overlay data on the data point adapted from Gadotti 2009. So the observed bulges are classified according to the Comedy relation. Here we show the surface density versus effective radius, mass of bulge versus effective radius, and the therapeutic index versus bulge to total ratio. And the black, red, and blue points represents elliptical galaxies, classical bulges, and pseudo bulges. So here are the basic point is like the pseudo bulges may evolve toward the same scaling relations as classic bulge via the destruction of short bars. And it is worth mentioning that the absolute position of the models on scaling are determined by arbitrary scaling factors. So the most physically meaningful comparison is the relative evolution. Therefore, the growth of bulge driven by destruction of short bars may be significantly blur the difference between pseudo bulges and classical bulges, and some relatively less massive and compact classical bulges may form via secular evolution due to the destruction of short bars. And here we also show the evolution of these bulges on black hole mass versus bulge mass relation, and the black hole mass is versus velocity dispersion relation, which also shows some similar effect, but maybe not that strong. And then we study the kinematics. So similar to the previous figure, so we show the evolution of the rotational velocity dispersions in different directions, and the anisotropic parameter. So basically, you could see some increase of sigma z and the decrease of the anisotropy parameter, which basically means that the spheroidal structure is more dominated by random motions, i.e., we form a bulge after the short bar is destroyed. And here is the some snapshots of the of sigma z. which also shows some similar behaviors for these two models. You could see a more spherical structure. Well, for the third models, it's more like a bar. So as a summary here, we provide a potential evolutionary channel that allows disks to evolve into classical like bulges without mergers. This is illustrated in this figure. So first, short or inner bar forms spontaneously when a dynamically cool inner disk exists. Such an inner disk may be built up gradually by gas funneled inward due to some perturbations from a large-scale bars. And then the short bars have been hypothesized to be an important mechanism for driving gas inflows within like 100 parsec scale, efficiently feeding black holes. Then the black hole is destroyed by the destroyed bar. So according to the results of the study, the remnants of the short bars have some properties similar to those of classical bodies. So therefore, an inner core disk bar can be transformed into a classical bulge under the influence of black hole. And the classical bulges forming by this mechanism are likely to be younger and more metal-rich than typical classical bulges. So it is possible that classical bulges with young stellar populations formed from the destruction of the short bars. And it is worth mentioning that the short bars invoked in our scenario need not to be as stable and long-lived as those of our models. And this effect could also be important. So basically, here is the conclusion. So some short bars are an important mechanism for driving gas inflow to feed the central black holes. And an initially boxy or peanut-shaped bulge with a small Slutsig index can be transformed into a more massive and compact isotropic slowly rotating sphere. And this bulge bears many of the characteristics of a classical bulge, including the location on bulge scaling relations. So to conclude, this is probably a new channel for forming classical bulges from the destruction of short bars formed from nuclear disks without some other effects like major mergers or something like that. And thank you very much. Thank you very much, and comments are welcome. Maybe I can stop here. Thank you.